Hello, today I want to explain about the application of extreme value theory, and in this case I want to explain particularly for disaster risk. So, if you heard phrase like once in 100 year disaster or similar, are there really have 100 years worth of data to prove that or something like that? Oh yeah, and usually you will use this technique to, yeah, for example, you work in insurance company or you want to build a bridge or dam. Of course, you want to calculate the extreme occurrence, right? So that is one or two the use of this technique. Now I want to explain this. I will explain the theory along with the script. The first step is to find the threshold from total and data. And in this case, in my script in here, here, this is the data. The column in here is for the months and the row for the days. Yeah, the days. But as you can see here, it's not just 31 rows, right? It's rows until 1054. So actually, it's quite complicated. So yeah, this is the months and this is the days. So after 31, this is after 31. For example, in here 32. This is the next year data here. So maybe you will understand if I show you the real Excel. Yeah, actually this is the rainfall data for Bengkulu here, because it just too much to read this in the script, so I just transform from this Excel dataset to this TSV dataset. TSV means tip top separated. Yeah, it's just like CSV but using tab. Okay, so in here we find the threshold. To find the threshold, actually you can just set it arbitrarily, but the recommended way is using the plot, the mean residual life plot like this. Actually, I have already prepared the script, and in the most of the case, you will plot the value from percentile 80 to percentile 99. Yeah, as you can see here, actually what we want to find is some flat plot, but as you can see here, there is no flat plot. But I think the good or the fittest value for this case is around 40 in here. Yeah, around between 30 and 40, but I prefer 40. So that's why in here I choose 40. Yeah, the theory about this is quite long, but the point is just choose where the flat line comes when you plot that, or just find the peak of the data. Oh yeah, I forgot explain about the x and y in here. So the x here is the percentile, and the y in here is mean excess over threshold. So it's the mean of the exactness. It's related to the step 2 actually, to find the difference value with the threshold where all number used to bigger than the threshold. So basically the number of the data for this step 2 will not same with the total data. It will be less than. So that's why in here we just name it as small n, and in here capital N. Oh, for the script, this is the part of the here, one line like this. And the third step is count the number of step 2. So basically we need to find the value of n, small n in here, and use it to calculate the probability of accidents using this formula. Basically it's like this. Here the probe line in here in the 79 line, and actually because we have daily data oh yeah, I forgot to mention about this. So in this case I want to calculate once for every 100 years precipitation. So that's why, because this is a daily data, then we need to, for the numbers t capital in here, for the numbers of t, we need to multiply 100 with 365. 365 is the numbers of days in 1 year, right? And in here you might think that, hold on, we what's the use of find the difference value for the threshold? What the use of find the difference with this threshold? Why we just need to the total of the number that surpass the threshold? What's the use of this? Actually the use of this is we will use it for the last step in here. So we need to find the number of return value of, or the number of the precipitation that will only happen once for every 100 years. So the formula is the threshold, in this case it's 40 plus the value to be expected that will only occur with probability 1 per t. So that's why we need to convert from probability value to precipitation. So that's why we need to calculate this difference, because we will fitting the value from that value, fitting the value from there. We basically we put all of the value of the x-dash in this histogram and then fit them to fitting function to find the Pareto distribution, the fittest Pareto distribution. And for every Pareto distribution, it have two properties like this, shape and scale. And actually this is the formula for the Pareto distribution. As you can see here, we have two parameters, and actually the formula in here, there's a typo. Actually this is sigma, because in here this is the formula when the shape is 0, like this. And as you can see here, the shape, it influence the shape. For the shape, like its name, it influence the shape of the line in here. And for the scale, it's for the range of the value for this Pareto distribution. So that's why we could find the value of the precipitation from this graphic. And the step for that is in here. From this function we find the shape and the scale Actually, for the location, most of the time it will be 0. If you're curious, this is the impact of different shape. So usually the shape range it varies from -1 to 1. So here I plot from -0.5 to 0.8, and as you can see here, for the negative value it just cut off like this, and for the 0 value it almost like a cutoff, like a negative value, but actually this is the asymptotic. I forgot. Actually, it's like this, a line that will getting closer and closer, but actually it will never meet. And for the positive value like this, it will be go beyond infinity. It will never meet 0. Basically, it's something like this. So here, this is the script, and if you want to plot the effect of shape, I already prepared them in here. Okay, let's just calculate for the for the calculation of the ones for every 100 years precipitation in Bengkulu. Okay, this is the Pareto distribution, and the result is looks like the estimated 100 years return level, or once, or the precipitation that will probably only occur once for 100 years is 388 millimeter. And yeah, so just that's it. It's pretty simple, but I think it will be quite useful in some case. So yeah, bye.